Welcome to the Deep Dive, the place where we take the essential sources governing our modern world and really distill them down to pure, actionable insight.
That's the goal.
Today, we are pulling back the curtain on, well, some pretty critical technology, stuff that underpins billions of dollars in trade, keeps chemical plants safe.
And manages every unit of energy flowing through our grids. It's fundamental.
It really is.
That's right. We're diving into let's call it the technological backbone of serious industrial process control.
Right.
I mean, if you're buying, selling, or processing high-value fluids, think steam, natural gas, maybe proprietary chemicals.
Right. Stuff where accuracy really matters.
Exactly. Your profit and, importantly, your regulatory compliance, it all depends entirely on the kinds of devices we're discussing today.
So our mission today is pretty clear then. First, we want to unpack the sophisticated multivariable pressure transmitter, the MVPT.
The brain of the operation, in many ways.
Yeah, seems like it. This is the device that turns simple measurements into, well, economic reality.
Couldn't have put it better.
And second, we need to explore the foundational components that feed this brain. The actual sensors doing the groundwork.
The eyes and ears, if you will. Specifically, the three main temperature sensor technologies. Resistance temperature detectors, or RTDs.
Okay.
Thermocouples, and thermistors, each with its own strengths and weaknesses.
Right. And the core concept here, it seems, is this shift, moving beyond just measuring, say, volume.
Precisely. It's about calculating true mass and energy flow. We're moving past those old, simple analog gauges.
Towards integrated smart systems.
Yeah, systems that use real-time physics, right there in the field to give you these vital, actionable metrics.
So this is where simple measurement becomes the foundation of, well, profitable commerce, like you said.
Absolutely. And safe operation, too. Let's not forget that.
Okay, let's unpack this then, starting with the MVPT itself. When we talk about this advanced device, it's definitely not just a fancy name for a standard pressure sensor, is it?
Oh, far from it. No. Think of the multivariable pressure transmitter as the consolidation expert of the industrial measurement field.
Consolidation expert, I like that.
It's an advanced transmitter, and its key feature is integrating measurements that historically would have needed, well, multiple separate instruments.
Right, like 3 different boxes on the pipe.
Exactly. 3 instruments, 3 separate wiring runs back to the control room, 3 separate maintenance schedules. You get the picture.
Okay, so what are these 3 specific variables that the MVPT brings together? And maybe, just give us a quick idea of why each one matters.
Sure. So typically it measures, first, differential pressure, or DP.
DP.
This is really the engine of flow measurement. It measures the pressure drop across some kind of restriction in the pipe, like an orifice plate. And that drop tells you about the fluid's velocity.
Got it. Pressure drop equals speed, essentially.
In a way, yes. Second, it measures static pressure. Think of this as the overall system pressure, the baseline pressure the fluid is under.
And why is that important?
Because pressure affects density, especially in gases and steam, so you need that context.
Okay, makes sense. DP for velocity, static P for context. What's the third?
And third, crucially, temperature T. This one is absolutely vital because temperature drastically affects fluid density, too.
Right. Hotter fluids are generally less dense.
Exactly. So temperature helps tell us the true weight or mass of what we're actually moving through that pipe, all measured by this single device.
But the real magic, you're saying, isn't just seeing those 3 numbers, DP, static P, T, side by side. The MVPT actually calculates things from them. Derived variable.
Precisely. That's where the intelligence lies. It has an internal processor, quite powerful, actually. It doesn't just report the raw data. It uses those real-time inputs, the DP, the static pressure, the temperature, and applies standardized equations, often based on physics principles.
Like Bernoulli, you mentioned.
Exactly. Derivations based on Bernoulli's principle for flow, or steam tables for energy calculations. And it uses these to calculate critical economic metrics, things like mass flow or energy flow.
Wow. So essentially running complex physics calculations right there in the field, at the point of measurement. That's quite a step up.
It really is. It's distributed intelligence.
How does that integrated approach actually function, like inside the box?
Well, the working principle is highly efficient. You've got these integrated sensors feeding the raw data DP, static P, T to the device's processor.
Okay.
And this processor, it's loaded with the necessary mathematical models. It crunches the numbers based on those classical physics principles we mentioned,
Right.
and determines the resultant mass or energy flow almost instantly. real-time calculation.
Let's contrast this, maybe make it clear.
Yeah.
Compared to the older way, the standard DP transmitter. What's the key difference?
Well, the difference is stark. A standard DP transmitter, it measures only differential pressure. That's it.
Just the pressure drop.
Just the pressure drop. Now, if you're measuring something simple and stable, like, say, water at a constant ambient temperature, then maybe measuring just DP is fine for calculating volumetric flow like gallons per minute.
Okay.
But, and this is a big but, if you're moving compressible fluids, things like steam or natural gas,
Which is common in industry.
very common. Their volume changes wildly with temperature and pressure. So volumetric flow alone is almost meaningless from an energy or mass perspective.
Oh, okay.
The multivariable approach, by adding that necessary temperature and static pressure data, gives you the comprehensive inputs you need to calculate the real, actual mass or energy content of the substance flowing, not just how much space it takes up.
That makes perfect sense.
Okay.
So why would a plant invest in this added complexity? Let's talk advantages. Efficiency, accuracy, and the money aspect.
Right, the practical advantage. Well, it often starts with total cost of ownership, or TCO.
TCO, okay.
Now, the initial sticker price of an MVPT, yeah, it might be higher, maybe, say, 3 times the cost of a single basic DP transmitter.
Seems like a lot up front.
It does. But then you factor in the installation. Instead of 3 separate instruments, you install 1. You reduce 3 long, complex wiring runs down to just 1. You simplify the control cabinet connections. You cut down commissioning time significantly.
Okay, I see the savings starting to add up there.
Exactly. There are studies, actually, that show over a typical 5-year lifespan, the TCO for an MVPT system can easily be 30% lower than installing, wiring, and maintaining 3 separate devices to get the same information.
30% lower TCO. That's substantial. So that covers the operational efficiency. What about the accuracy gains?
Yeah.
Especially in, high-stakes situations.
This is arguably even more important. It brings us to something called custody transfer.
Custody transfer. Sounds official.
It is. It's the point where ownership of the fluid literally changes hands, like selling natural gas from a pipeline company to a local utility, or selling steam from a power plant to a neighboring factory.
Cash register moment.
Precisely. And in those situations, the accuracy requirements are incredibly stringent. Legally binding, often. You must know the exact mass or energy being transferred. Volume just doesn't cut it.
Because of those density changes we talked about.
Exactly. Think about it. A typical chemical plant selling steam. We've seen cases where a temperature measurement error of just 0.5 degrees Celsius.
0.5 degree. Seems tiny.
Tiny, right. But it can translate to a $50,000 per month discrepancy in billing due to the miscalculated mass flow. $50,000 a month from 0.5 degree.
Wow. Okay, now I see why the MDPT isn't just a convenience. It's a financial and legal necessity.
It really is. Absolutely required in those high-stakes environments. Chemical plants, petrochemical, power generation, oil and gas pipelines, anywhere big money or strict regulation is involved.
Okay, the efficiency and accuracy arguments are compelling.
Yeah.
But you mentioned complexity earlier. What are the trade-offs? It can't be all upside.
No, you're right. You're essentially trading mechanical simplicity for computational power and integration. And that comes with its own challenges.
Such as?
Well, the MVPT demands more specialized attention. Its initial configuration is definitely more complex. You're not just setting a range for 1 variable. You're inputting parameters for 3 variables, defining the fluid properties, setting up the specific flow equations.
More buttons to push, more settings to get right.
Pretty much. And calibration isn't just checking one sensor. It's verifying the DP, static pressure, and temperature inputs are all accurate and working together. Diagnostics are also more integrated and potentially more complex.
So you need more highly trained technicians.
Often, yes. You really need operators and technicians who understand the intricate interplay between DP, static pressure, and temperature, and how they affect the final calculated flow number, not just someone who reads the final output.
That's a really crucial insight. There's a risk, maybe, of over-reliance on that final calculated number.
Exactly.
Without understanding the raw data that goes into it.
That's precisely the risk. You need proper training to prevent a loss of, let's call it, situational awareness. If the MVPT suddenly reads a high flow, is it a real process change? Or did the integrated temperature sensor maybe fail high, causing the MVPT to miscalculate the fluid density and report a high flow incorrectly?
Right. You need to be able to troubleshoot the inputs, not just trust the output blindly.
Absolutely critical.
Let's focus on that temperature input again. We've established it's non-negotiable for calculating mass flow accurately.
Oh,
Can you give us a clearer analogy maybe for why it's so vital?
okay, sure. Let's use an analogy. Imagine you're buying, say, natural gas, maybe in a cold climate.
Right.
If the seller only measures the volume of gas delivered, the volumetric flow, they're essentially charging you for a certain amount of space the gas occupies. Let's say 1,000 cubic feet.
Okay, 1,000 cubic feet of gas.
Right. But natural gas is compressible. If it's a really cold day, that gas is very dense. Those 1,000 cubic feet are packed tightly with molecules, meaning they contain a huge amount of energy, a lot of actual mass.
Got it. More bang for your buck if you're the buyer.
If you're the buyer paying by volume, yes. But now, imagine it's a hot day, the gas expands, becomes much less dense. That same 1,000 cubic feet of space now contains significantly fewer molecules, less actual mass, and therefore less energy content.
Ah, so if you're the buyer paying that same price for 1,000 cubic feet on a hot day, you're getting less energy, effectively losing money compared to the cold day.
Precisely. Paying by volume alone is inaccurate and unfair when density changes. Mass flow measurement corrects this entirely.
No.
Because mass flow always ensures you're measuring, and therefore paying for, the actual mass, the weight, the number of molecules, the true energy content of the fluid, regardless of how much it expands or contracts due to temperature or pressure changes.
So mass is constant, volume isn't.
That's the key. That's why accurate real-time temperature and pressure inputs are absolutely non-negotiable for correct mass flow calculation, especially in those high-variance applications like steam and gas.
Okay, crystal clear now. And this leads us directly to another critical concept you mentioned that ties all three variables together: dynamic compensation. What exactly is that, and how does it work inside the MVPT?
Right, dynamic compensation. This is really the MVPT's superpower. It's its ability to continuously, instantly adjust its flow calculations based on those instantaneous changes in the process conditions.
Adjusting on the fly.
Exactly. Imagine steam flowing through a pipe again. Maybe the boiler pressure drops slightly, causing the steam pressure to dip. At the same time, maybe the temperature rises just a fraction of a degree.
Okay, typical process fluctuations.
Right. Those changes, the lower pressure, the higher temperature, are fed simultaneously in real time into the MVPT's processor.
Yeah, man.
The device immediately recalculates the steam's density based on those new current inputs using its internal steam tables or equations. And based on that new density, it instantly adjusts the reported mass flow figure.
So it's not using some static assumed density value.
Absolutely not. It's using the density that corresponds to the actual measured pressure and temperature at that very moment. That's the dynamic part.
It's that continuous, instantaneous adjustment that ensures both accuracy, especially for billing, like we discussed, and also responsiveness to the often volatile nature of industrial processes.
Precisely. It prevents those errors from accumulating. It keeps the measurement true to the real conditions, second by second.
Now, an MVPT doesn't just magically measure flow in an empty pipe, right? It needs that restriction we talked about to measure the differential pressure. This brings up the mechanical side, the primary flow elements.
Ah, yes, a vital connection point. It often gets overlooked when focusing on the smart transmitter.
The transmitter is measuring the effect of flow.
But the primary flow element is what creates the measurable effect. It creates the necessary conditions for that DP measurement. The MVPT itself is typically mounted with tubing connecting its high and low pressure ports across one of these primary elements installed in the pipe. Common examples are things like an orifice plate, a venturi tube, or maybe a flow nozzle.
Let's take the simplest one, the orifice plate. What exactly is its role in this system? How does it work?
The orifice plate is basically just a thin metal plate with a precisely machined hole, a specific size, in the center. You install it in the pipe, perpendicular to the flow.
So it's like putting a dam with a small hole in the river.
Kind of. When the fluid flows through the pipe and hits that restriction, the smaller hole, it has to speed up to get through.
Makes sense.
And according to Bernoulli's principle, when fluid velocity increases, its pressure decreases.
Oh, okay.
So the MVPT uses its differential pressure sensor to measure the higher pressure upstream of the plate, before the restriction, and the lower pressure right downstream of the plate after the restriction where the fluid is moving faster.
And the difference between those two pressures is the DP signal.
Exactly. And the magnitude of that DP, that pressure difference, is mathematically proportional to the flow rate squared, actually.
Okay, so the MVPT measures the DP created by the orifice plate,
Right.
calculates a basic flow rate from that DP based on the plate's known dimensions.
Yes.
And then it corrects or refines that calculation using the static pressure and temperature inputs which is also measuring right there at the same point, to account for the fluid's actual density.
You've got it perfectly. It integrates the physical measurement of the restrictions effect, dP, with the necessary physical properties of the fluid itself, density, which is affected by P and T, to produce that final accurate mass or energy flow output.
So it's the combination of the mechanical restriction, the multiple physical sensors, and the computational brain that really defines a modern, accurate flow measurement system.
Absolutely. You need all those pieces working together seamlessly.
Okay, we've established the MBPT as this powerful brain calculating mass flow, but as was stressed, it's entirely dependent on the quality of that temperature signal it receives.
Utterly dependent. Garbage in, garbage out, as they say.
Right. If that T variable is off by even half a degree, as in your example, the entire mass flow calculation is compromised, potentially costing a fortune.
Or leading to safety issues, depending on the process.
True. So now let's dive into those eyes and ears, the foundational temperature sensors themselves. We should start with what many consider the gold standard for stability and precision, the resistance temperature detector, or RTD.
The RTD. Yes, this is the sensor you choose when repeatable precision is the absolute top priority.
And how does it work? What's the principle?
Its working principle is based on a very fundamental property of certain metals. Their electrical resistance changes predictably with temperature.
Sure.
Specifically, for the metals used in RTDs, overwhelmingly platinum in industrial settings, as the temperature increases, the electrical resistance increases.
Resistance goes up with temperature.
Right. This is classic positive temperature coefficient behavior, or PTC. More heat, more resistance.
And the benchmark we always hear about in industry is the PT100. What does that standard actually signify?
Right, PT100, it's really a definition of the sensor's baseline performance and material. PT stands for platinum.
Why platinum?
Platinum is prized for its excellent chemical stability. It doesn't corrode or oxidize easily, and its very linear and repeatable resistance-temperature relationship over a wide range.
Okay, so PT for platinum. What about the 100?
The 100 means that the device has an electrical resistance of exactly 100 ohms when the temperature is exactly 0 degrees Celsius, 32 degrees Fahrenheit.
It's a calibration point.
Exactly, it's a standardized reference point. This standardization is what allows for its exceptional accuracy and repeatability. You know exactly what resistance to expect at a known temperature.
Now, RTDs are famous for accuracy, but you hinted that this precision comes with a catch, especially regarding the wiring. Why do we need different wiring setups, like 3-wire and 4-wire? Why does the resistance of the connecting wires matter so much?
Ugh. This is absolutely crucial for understanding RTD accuracy in the real world. The challenge is this. The platinum sensing element itself might be very precise, say 100 ohms at 0 degrees C.
Right.
But you need to connect that sensor, which is out in the hot or cold process pipe, back to the transmitter or control system, often many meters away, using copper wires.
Standard copper wires.
Standard copper wires. And those long copper lead wires also have electrical resistance.
Yeah.
And worse, the resistance of those copper wires changes slightly with the ambient temperature changes in the plant environment where the wires are run.
So the wires themselves act like little inaccurate temperature sensors.
In effect, yes. If you don't compensate for that lead wire resistance, the transmitter reading the total resistance will mistakenly include the resistance of the wires in its calculation.
So it thinks the platinum element is hotter than it really is because it's adding the wire resistance.
Exactly. It artificially inflates the temperature reading. This is why the simplest configuration, the 2-wire RTD, where the transmitter just measures the total resistance of the sensor plus the 2 lead wires, is inherently the least accurate. It's only suitable for non-critical applications or where the leads are very short.
Okay, so 2-wire is out for precision work. How do 3-wire and 4-wire solve this problem?
They use clever differential measurement techniques. The 3-wire RTD is the most common solution you'll find in industry. It's a good balance of accuracy and cost.
How does it work?
It uses 3 identical lead wires. The transmitter sends a measurement current down one wire through the RTD element and back up a second wire. The third wire is connected to one side of the RTD element but doesn't carry the main current.
Okay, what does the 3rd wire do?
The transmitter uses the 3rd wire essentially to measure the voltage drop across one of the current-carrying lead wires. Since all 3 wires are assumed to be identical in length and resistance, the transmitter can mathematically subtract the resistance of both current-carrying lead wires from the total loop resistance.
It measures the error on one wire and assumes the other is the same, then subtracts it out.
Pretty much, yes. It effectively neutralizes most of the lead wire resistance error, providing much better accuracy than a 2-wire setup.
But you mentioned the absolute peak of precision is the 4-wire configuration.
Yeah.
How does that achieve almost perfect compensation?
Right. The 4-wire RTD is the gold standard. You use this for laboratory work, calibration standards, and the most critical high-precision process control loops. It completely eliminates the lead wire resistance from the measurement calculation.
Oh.
It operates on a true potentiometric or bridge measurement principle. 2 wires are used exclusively to supply a very small, constant excitation current through the RTD element.
Okay, power supply wires.
Right. The other 2 wires are connected directly across the RTD element itself, and these wires are used only to measure the voltage drop across the platinum element caused by that excitation current.
So they're just sensing wires, carrying almost no current themselves. Exactly. Because these voltage-sensing wires carry virtually no current, the resistance of these wires themselves causes no voltage drop, and therefore doesn't affect the measurement. The transmitter is reading the true voltage drop across the RTD element alone.
Which is directly proportional to the RTD's resistance and thus its temperature without any wire error.
Precisely. It completely cancels out the effect of the lead wire resistance, no matter how long the wires are or how much their temperature changes.
That's really elegant engineering, using the wires to cancel out the error caused by the wires themselves.
It is quite clever.
You also mentioned something called the Callendar-Van Dusen equation earlier. Is that related to this? What's its practical relevance? Why should, someone listening care about a specific equation?
The relevance is all about standardization and ensuring reliable, interchangeable accuracy across the globe. Platinum's resistance change, while very stable and repeatable, isn't perfectly linear over its entire wide operating range.
It's slightly curved, the resistance versus temperature graph.
Exactly. It's a well-defined curve, but it's not a straight line. The Callendar-Van Dusen equation is the internationally accepted, standardized mathematical formula that accurately describes this nonlinear relationship for industrial platinum RTDs, like the PT100.
So the transmitter uses this equation?
Yes. Smart transmitters and control systems have this equation, or coefficients derived from it, programmed in. When they measure the resistance of the PT100, they plug that resistance value into the Callendar-Van Dusen equation to calculate the precise corresponding temperature.
And because it's standardized.
It ensures that if you buy a certified PT100 sensor from manufacturer A in Germany and connect it to a transmitter from manufacturer B in the US, they will both use the same fundamental relationship defined by this equation. This guarantees consistent, accurate temperature readings according to the International Temperature Scale, ITS 90, which is vital for scientific work and high-precision industrial processes.
Okay, so standardization for reliable accuracy. Got it. Given all this high stability and precision engineering, where do we typically see RTDs used? And what are the inevitable downsides or trade-offs?
Well, as we said, they're the preferred choice for applications demanding high accuracy, repeatability, and stability over long periods. Think pharmaceutical batch validation, fine chemical reactions, custody transfer points for some fluids, efficiency calculations in power plants, places where a small error is costly or unacceptable.
Makes sense. What are the downsides?
The main trade-offs are typically cost, response time, and mechanical robustness. RTDs, especially high-accuracy 4-wire ones, are generally more expensive than other sensor types like thermocouples.
Okay.
They also tend to have a slower response time. The platinum element itself, often a wire coil wound on a ceramic core, has more mass than, say, a thermocouple junction, so it takes longer to heat up or cool down to the actual process temperature.
So maybe not ideal for very rapidly changing temperatures.
Potentially not if millisecond response is needed. And finally, they can be more sensitive to mechanical shock and vibration. That platinum coil is somewhat delicate. Dropping an RTD probe can easily damage it or shift its calibration.
Which is why proper mounting is key. You mentioned thermowells earlier.
Absolutely essential. RTDs are almost always installed inside a protective metal sleeve called a thermowell, which shields them from the process fluid's pressure, flow forces, and corrosion. But that thermowell adds even more mass and further slows down the response time. It's a necessary compromise for protection.
You mentioned a failure scenario earlier involving 2-wire RTDs and ambient temperature swings.
Ah, yes. That was a classic case. A plant manager trying to save a bit of money on wiring for a mixing tank temperature measurement. The tank area had pretty significant ambient temperature swings between day and night, maybe 10, 15 degrees C.
Okay.
They were using simple two-wire RTDs with long cable runs back to the control room. They couldn't figure out why their product batches were inconsistent, sometimes reacting too fast, sometimes too slow.
And the cause was?
The uncompensated resistance change in those long copper-lead wires. As the ambient temperature in the plant changed, the wire resistance changed, adding a varying error of nearly 2 degrees Celsius to the actual tank temperature reading.
Wow. So their control system was basing critical reaction timing on temperature data that was off by up to 2 degrees, purely due to the wiring and ambient changes.
Exactly. A perfect illustration of why you pay for 3-wire or 4-wire compensation in critical applications. Cutting that corner costs them far more in wasted product than the wiring would have.
A powerful lesson. Okay, let's pivot now. If RTDs are the precision and stability champs, let's talk about the speed and range champions. Thermocouples. These sound like the rugged survivors of the sensor world.
That's a good way to put it. Thermocouples, often abbreviated TC, are chosen when you need to measure very high temperatures, respond very quickly, or survive in harsh, demanding environments where an RTD might fail.
And they work on a completely different physical principle, right?
Yeah.
Not resistance change.
Completely different. They operate based on the Seebeck effect, discovered back in the 1820s.
Seebeck effect. Okay.
This is a fundamental thermoelectric phenomenon. It states that if you take 2 wires made of different dissimilar electrical conductors, say, one iron wire and one constant tan, a copper-nickel alloy wire, and join them together at one end.
Yeah, make a junction.
Right. And then create a temperature difference between that measurement junction, the hot junction, which you put in the process, and the other end of the wires, the cold or reference junction. A small electrical voltage will be generated across the open ends of the wires.
A voltage appears just because of the temperature difference across 2 different metals.
Exactly. A tiny voltage, usually in the millivolt range, but it's directly proportional to the temperature difference between the hot junction and the cold junction.
Fascinating. So instead of measuring changing resistance like an RTD, we're measuring a tiny voltage potential generated by the heat difference itself.
Precisely.
And what gives them the champion status for temperature range? Why can they handle so much more heat than RTDs?
It comes down to the materials. By choosing different pairings of metal alloys, you can create thermocouples that function reliably at incredibly high temperatures, far exceeding the limits of platinum RTDs.
Okay.
Thermocouples are categorized by type, based on their specific metal pairings, each with its own characteristics and temperature range. For example, the real workhorse in industry is Type K.
Type K. What's that made of?
It uses nickel chromium, often called chromel, for one wire, and nickel alumel, an alloy of nickel, manganese, aluminum, and silicon for the other. Type K is popular because it's relatively inexpensive, offers a wide temperature range, typically from around -200 degrees C up to about 1250 degrees C, or even 1350 degrees for short periods, and has a reasonably linear output.
Wow, 1250 degrees C. That's serious heat. Are there other common types?
Oh yes. Type J, iron constant tan, is also very common, good up to about 750 degrees C, but prone to rusting in humid environments because of the iron. Type T, copper constant tan, is excellent for lower temperatures, including cryogenics down to -250 degrees C, and very stable. Type E, chromal constant tan, has the highest voltage output per degree C, making it sensitive. And then you have noble metal types like Type S, R, and B, using platinum rhodium alloys, for very high temperatures, up to 1700 degrees C or even 1800 degrees C, often used in labs, glass manufacturing, or semiconductor processing.
So a whole family of options depending on the temperature range and environment.
Exactly. They cover the widest possible spectrum of industrial heat measurement, from deep freeze conditions right up to molten metal temperatures.
Now, you emphasize that the voltage generated depends on the temperature difference between the hot junction in the process and the reference end, the cold junction. This brings up a really critical, unique requirement for thermocouples. Cold junction compensation, or CJC. Why is this so necessary?
This is arguably the single most important concept to grasp about using thermocouples accurately. Remember, the Seebeck voltage only tells you the temperature difference between the hot end and the cold end.
Right. Hot minus cold.
Exactly. The cold junction is typically where the special thermocouple wires, like chromel and alumel for Type K, terminate and connect to the standard copper wires going into the transmitter or measuring instrument. This connection point is the cold junction.
Okay. So it's usually at the transmitter terminals.
Usually, yes. Now imagine the temperature at those terminals changes because the ambient temperature in the control cabinet or junction box goes up or down.
Yeah.
If the transmitter doesn't know the actual temperature of that cold junction reference point, the overall reading will be wrong. For example, if the hot junction is at 500 degrees C and the cold junction is at 25 degrees C, the thermocouple generates a voltage corresponding to a difference of 475 degrees C. But if the ambient temperature rises and the cold junction heats up to 35 degrees, the actual temperature difference is now only 465 degrees C. The thermocouple voltage will decrease accordingly. If the transmitter isn't aware that the cold junction temperature changed, it will incorrectly report a lower process temperature, even though the process itself hasn't changed at all.
Ah, I see. The measurement drifts with the ambient temperature at the connection point. So how do smart transmitters handle this? How do they perform cold junction compensation?
Smart transmitters have CJC built in. It's an electronic correction mechanism. They include a separate, highly accurate temperature sensor, often a small RTD, or, more commonly, a thermistor mounted directly on or very near the terminal block where the thermocouple wires connect.
So they measure the temperature right there at the cold junction.
Precisely. This reference sensor continuously measures the actual ambient temperature at the cold junction terminals. The transmitter's microprocessor reads this cold junction temperature, converts it into its equivalent thermocouple voltage contribution, based on the specific TC type being used, and then adds this voltage value mathematically to the raw voltage being measured from the thermocouple loop itself.
So it adds back the temperature difference that was lost due to the cold junction not being at absolute zero.
Effectively, yes. It compensates for the cold junction temperature, so the final output reading accurately reflects the temperature only at the hot measurement junction in the process, regardless of ambient temperature fluctuations at the transmitter.
It's like a continuous automatic calibration happening constantly in the background. Very clever.
It's absolutely necessary for any accurate thermocouple measurement. Without CJC, thermocouple readings would be wildly unreliable in most industrial settings.
Okay, let's talk reliability and failure modes. These sound rugged, but how do they typically fail, especially given their use at high temperatures?
Their primary failure mode, especially over time at high temperatures, is drift.
Drift, meaning they become less accurate.
Exactly. At very high temperatures, the metal alloys themselves can start to degrade. They can oxidize, corrode, or experience changes in their metallurgical structure due to prolonged heat exposure. This gradual degradation slowly changes the thermoelectric properties of the metals. The relationship between temperature and the voltage generated begins to shift, causing the thermocouple's reading to drift away from the true temperature, usually reading lower over time.
So they lose accuracy gradually and need periodic checking or replacement.
Yes, regular calibration checks are more critical for thermocouples than for RTDs, especially in high-temp or corrosive services. They don't usually fail abruptly like an RTD wire breaking. They just fade in accuracy.
Are there other issues? You mentioned grounding loops earlier when talking about MVPTs. Is that relevant here?
Very relevant. Thermocouples generate a very small signal, just millivolts. This makes them susceptible to electrical noise interference, and grounding loops are a common source of noise.
Remind us what a grounding loop is in this context.
A grounding loop can occur if the tip of the thermocouple, the hot junction, is electrically bonded to the metal pipe or vessel it's measuring. This is called a grounded junction thermocouple, often chosen for faster response.
Okay.
If that pipe or vessel is grounded somewhere and the measuring instrument or transmitter connected to the other end of the thermocouple wires is also grounded somewhere else in the plant's electrical system, you can create an unwanted secondary electrical circuit or loop through the ground connections.
Ah, like a short circuit through the earth.
Sort of. Stray electrical currents flowing through the plant's grounding system can then flow through this loop and induce noise voltages onto the tiny thermocouple signal wires.
Leading to unstable or inaccurate readings.
Exactly. You might see the temperature reading jumping around erratically or offset by a significant amount. Engineers often have to be careful with grounding strategies. Sometimes they choose ungrounded junction thermocouples, where the hot junction is electrically isolated from the protective sheath, or use signal isolators in the circuit to break these potential ground loops, especially in electrically noisy industrial environments like near large motors or variable frequency drives.
So thermocouples are rugged, fast, handle huge temperature ranges, and are cost-effective. But you trade off the inherent accuracy and long-term stability of an RTD, you absolutely need CJC, and you have to be mindful of potential drift and noise issues like grounding loops.
That's a perfect summary of the trade-offs.
Okay, what about the third sensor type you mentioned, thermistors? Where do they fit into this picture? They don't seem as common in heavy industry.
Thermistors are a bit different. They are essentially highly specialized resistors whose resistance is extremely sensitive to temperature changes, much more sensitive per degree than RTDs.
Highly sensitive resistors. Okay.
They are generally not standardized for core industrial process control in the same way RTDs and thermocouples are, but they are absolutely vital for specific niche applications where that high sensitivity is key.
And you mentioned they come in two main flavors based on how the resistance changes.
Yeah.
NTC and PTC.
Right. The most common type used for temperature sensing is the NTC thermistor, which stands for negative temperature coefficient.
Negative. So resistance goes down as temperature goes up.
Exactly the opposite of an RTD. As an NTC thermistor gets hotter, its electrical resistance decreases dramatically and nonlinearly.
Okay. And the other type?
The other type is PTC, for positive temperature coefficient. Like an RTD, its resistance increases with temperature. However, PTC thermistors often exhibit a very sudden, sharp increase in resistance at a specific threshold temperature.
A sudden jump. What's that used for?
Because of that sharp jump, PTC thermistors aren't typically used for precise temperature measurement over a range. Instead, they're commonly used as protective devices, resettable fuses, overcurrent protection in circuits, or over-temperature cutoff switches. When the threshold temperature or current is reached, their resistance spikes, effectively blocking current flow.
So PTC for protection, NTC for sensing. Got it.
Yeah.
What makes NTC thermistors so compelling for the applications where they're used?
Several things. First, as I said, high sensitivity. A very small change in temperature produces a very large change in their resistance, much larger than the change you'd get from an RTD for the same temperature shift. This allows for very fine temperature resolution.
Okay, high sensitivity. What else?
They're typically very compact in size. The sensing element can be tiny, like the head of a pin. This allows them to be placed in very tight spaces.
Small size.
That small size also contributes to their third advantage, potentially the fastest response time of all three sensor types. Because the sensing element has very little thermal mass, it can react extremely quickly to changes in temperature.
Fast response.
And finally, they are generally quite low cost compared to RTDs or even some thermocouples.
Okay, high sensitivity, compact, fast, and cheap. That sounds like a winning combination. Why aren't they used more widely in complex MVPT applications or general process control? What are the downsides?
The disadvantages are significant and generally limit their use in demanding industrial process control. First, they typically have a relatively narrow operating temperature range compared to RTDs and especially thermocouples. They don't handle extreme highs or lows well.
Okay, limited range.
Second, the resistance change is highly nonlinear, much more nonlinear than even thermocouples. This makes accurate linearization across a wide temperature span computationally intensive and difficult to standardize effectively. Different NTC thermistors, even of the same nominal value, can have quite different response curves.
So less interchangeable than RTDs or standard thermocouple types.
Much less so. Third, they generally suffer from poorer long-term stability compared to RTDs. Their resistance characteristics can drift over time, especially if exposed to higher temperatures within their range.
Less stable.
And finally, a really critical issue for accurate measurement is self-heating.
Self-heating, what does that mean?
Remember, to measure the resistance of any resistor, RTD or thermistor, the measuring instrument has to pass a small electrical current through it.
Right, the excitation current.
Yes.
Yeah.
Now, because thermistors are so sensitive to temperature and their resistance values can be quite high, even the tiny measurement current generates a small amount of heat within the thermistor element itself due to IOR power dissipation.
The current flow heats up the sensor.
Exactly. This self-heating artificially raises the temperature of the sensor element slightly above the actual ambient temperature it's trying to measure.
Which introduces an immediate error into the reading.
Precisely. To maintain accuracy, the measurement current passed through a thermistor must be kept extremely low, often much lower than for an RTD. This can limit the speed or resolution of the measurement, creating a trade-off. It makes them difficult to use reliably in dynamic industrial systems where you might need faster updates but can't tolerate self-heating errors.
Wow, that's a significant drawback for precision work.
Mm-hmm.
So where do we typically find thermistors used then?
Because of these limitations, you don't see them much in core process control loops like those involving MVPTs. They are much more common in applications like consumer electronics, monitoring temperature inside phones or computers, battery pack thermal management, preventing overheating during discharging, HVAC systems, thermostats, duct sensors, medical devices, and some specific automotive applications. Places where high sensitivity over a limited range is needed, cost is a driver, and the self-heating can be managed or tolerated.
Okay, that makes sense. So that gives us our 3 foundational sensors: the stable, precise RTD, the rugged, wide-range, fast thermocouple, and the highly sensitive, fast but limited thermistor, each with its own inherent flaws or characteristics to manage the area. RTD needs lead wire compensation, the TC needs CJC and linearization, the thermistor has nonlinearity and self-heating.
Exactly. And importantly, they all produce a raw signal, either a changing resistance or a tiny nonlinear millivolt signal that isn't directly usable by a high-level control system or an MBPT for complex calculations.
Right. The raw signal is noisy, nonlinear, needs compensation. It's not ready for prime time.
Precisely. We need something in between, a sophisticated translator, if you will. Something to take that raw, unstable resistance or that tiny millivolt signal and turn it into a clean, standardized, stable signal that's ready for those high-level computations or control decisions.
And that translator, that critical integration piece, is the smart temperature transmitter.
Exactly. This device typically sits out in the field, close to the sensor, acting as the intelligent interface between the raw sensor and the main control system, or the MVPT.
So what is its fundamental role? What does it actually do?
Its primary function is really twofold. First, it takes that raw, low-level sensor signal, the changing resistance from the RTD, or the millivoltage from the thermocouple, and it converts it into a standardized, robust industrial output signal. Most commonly, this is the ubiquitous 420 milliamp mA analog current signal.
The 420 mA loop, industry standard.
The absolute standard for basic process control signals. It's reliable, good for long distances, and relatively immune to electrical noise. But the smart transmitter does much more than just signal conversion.
Okay, what else? That sounds like what an older analog transmitter would do.
It is, but the smart transmitter adds digital intelligence. It performs complex processing on the signal before converting it to 420 mA, and it often supports digital communication protocols in addition to the analog signal.
Okay. So what are those crucial corrective processes it performs internally to clean up and standardize the sensor signal? You mentioned linearization and CJC before.
Right. The smart transmitter uses its internal microprocessor and memory to address those inherent sensor flaws we discussed. The first key process is sensor linearization.
Linearization, making the signal straight.
Exactly. As we established, thermocouple output is particularly nonlinear. Its voltage doesn't increase in a perfectly straight line as temperature goes up. RTDs are better, but still not perfectly linear over their full range.
Right.
The smart transmitter has sophisticated lookup tables or mathematical polynomial equations stored in its memory, specific to the type of sensor connected, e.g. type K thermocouple curve, or the Callendar-Van Dusen equation coefficients for a PT100 RTD. It takes the raw resistance or millivolt reading, applies the appropriate linearization algorithm, and calculates a precise linear temperature value. It effectively straightens out that curve, ensuring that a 1-degree change results in the same signal change whether it's at 100 degrees or 500 degrees.
So it provides a consistent linear temperature reading to the control system, regardless of the sensor's quirky behavior.
Precisely. That's critical for accurate control. And the second crucial correction specifically for thermocouples is that cold junction compensation, CJC, we detailed earlier.
Right, accounting for the temperature at the transmitter terminals.
Yes. The smart transmitter uses its internal reference sensor to measure the temperature of the cold junction terminal block, and it electronically adds the equivalent temperature offset to the compensated thermocouple reading.
So it delivers an absolute temperature reading, not just a relative difference.
Correct. It handles both the linearization and the CJC internally, presenting a clean, accurate, absolute temperature value ready for output.
Okay, so it corrects the fundamental flaws. But the word smart usually implies more than just correction. What are the key advantages of using a modern, smart digital transmitter compared to those older, purely analog ones that just did the 420 mA conversion?
The advantages are significant, especially regarding diagnostics, connectivity, configuration, and overall system maintenance. They fundamentally change how you interact with field instrumentation.
How so?
Well, an older analog transmitter just gave you that 420 mA signal, a single unverified number representing the temperature. That's all.
Okay, just measurement.
Right. A smart transmitter still provides that robust 420 MA analog signal, often needed for fast, reliable connection to safety systems or basic controllers. But critically, it adds a digital communication layer on top of, or sometimes instead of, the analog signal.
Digital communication, like network connectivity for the sensor.
Essentially, yes. It supports standardized industrial communication protocols. The most common one, especially for upgrading existing plants, is HART. Others include Foundation Fieldbus and Profibus PA, which are often used in newer, fully digital installations.
Okay, HART, Fieldbus, Profibus. What does this digital connectivity actually let you do?
It opens up a world of possibilities. Because the communication is digital and often bidirectional, you can, first, remotely configure the transmitter. Set the sensor type, the temperature range, damping values, tag names, all from the control room or a handheld communicator without having to physically go out to the device and fiddle with tiny switches or potentiometers.
That saves a lot of time and hassle, especially if the transmitter is in a hard-to-reach or hazardous area.
Immense time saving and much safer. Second, you can perform advanced diagnostics.
Diagnostics, like check if it's working.
Much more than that. The smart transmitter is constantly monitoring not just the process temperature, but also the health of the sensor itself and its own internal electronics.
What kind of health checks?
It can detect things like sensor burnout or open circuit, sensor drift, comparing against historical data or dual sensor inputs, degradation of thermocouple insulation resistance, wiring faults, like detecting if a 3-wire RTD compensation is failing, internal electronic faults, or even if the process temperature has gone outside its configured range.
Wow. So it can tell you why a reading might be bad, not just that it's bad.
Exactly. It provides diagnostic codes and alerts that pinpoint the likely cause of a problem. This drastically speeds up troubleshooting.
And this leads to better maintenance.
Absolutely. It enables predictive maintenance. Instead of waiting for a sensor to fail completely and potentially shut down your process, reactive maintenance, the smart transmitter can alert you to subtle signs of degradation before failure occurs.
Like that thermocouple drift you mentioned.
Right, or increasing noise on the signal. You get an early warning, allowing you to schedule the sensor replacement during the next planned maintenance outage, rather than dealing with an emergency crisis. This improves uptime and reliability significantly.
And finally, remote calibration.
Yes, often you can perform remote calibration checks or trim the calibration, make fine adjustments digitally, again without needing to be physically present at the device with calibration baths. It streamlines the whole validation process.
So the smart part is really about the added intelligence, the communication, the diagnostics, the remote access, leading to better accuracy, easier configuration, and much more efficient maintenance.
That sums it up perfectly. It's a huge leap beyond just sending an analog current signal.
Okay, let's spend a bit more time on that digital communication layer, because choosing the right protocol, like HART versus Fieldbus, seems like a major decision for engineers designing or upgrading a plant. Can we compare those two heavyweights?
Definitely. HART and Foundation Fieldbus, often just called FF, are probably the two most dominant forces, but they represent quite different philosophies and have different strengths, especially concerning installation and control strategy.
Let's start with HART. You said it's common for upgrades. Why?
HART stands for Highway Addressable Remote Transducer. It's genius, and the reason for its massive installed base lies in its backward compatibility and non-intrusive nature.
How so?
It was specifically designed to work over the existing traditional 420 metal A wiring that plants already had installed for their older analog transmitters.
Ah, so you don't need to rip out all the old wires to get the smart benefit.
Exactly. That's the key for brownfield sites' existing plants. HART cleverly superimposes a low-level, low-frequency digital signal right onto the same pair of wires, carrying the 420 MA analog signal. It uses a technique called frequency shift keying, FSK, basically toggling between two frequencies to represent digital ones and COs.
So the analog signal is still there, doing its job.
Yes, the core 420 analog measurement signal remains intact and functions just as reliably as before, providing the primary process variable to the control or safety system, often with faster updates than the digital signal.
But you also get the simultaneous digital channel.
Right. The digital HART signal provides that slower but bidirectional communication path for all the smart stuff. The remote configuration, the detailed diagnostics, the calibration trims, device status information, even secondary process variables sometimes.
And you access this digital info using a special handheld communicator or interface software.
Correct. You can connect a HART communicator anywhere along that 420 milli loop without interrupting the analog signal and talk digitally to the specific device you want. Each HART device has a unique address.
So HART is the perfect hybrid. Robust analog control signal plus smart digital diagnostics all over existing wiring.
That's why it's been so incredibly successful. It provided an evolutionary path to smarter instrumentation without requiring a revolutionary rewiring of entire plants.
Okay, now contrast that with Foundation Fieldbus. You said it's more for greenfield sites, new plans.
Right.
How's it different?
Foundation Fieldbus, FFH1 is the relevant version here, takes a radically different, fully digital approach. It completely eliminates the 420 MA analog signal.
No analog signal at all.
None. Everything, the process measurements, the diagnostic information, configuration data, even the power to operate the field devices flows digitally over a single twisted pair of wires. It's a true, all-digital, multi-drop network segment running out into the field.
Wow. What are the advantages of going fully digital like that?
The potential benefits are significant. First, richer data. Because it's fully digital with higher bandwidth than HART's overlay, you can get much more information back from each device, multiple variables, complex diagnostic blocks, status flags, all communicated digitally.
Okay.
Second, and perhaps more fundamentally, FF enables control in the field, CIF.
Control in the field, what does that mean?
It means that the field bus devices themselves, the transmitters, the valve positioners can have control algorithms like PID loops executed directly within them. They can communicate peer-to-peer on the field bus segment and perform local control functions without needing every signal to go back to the central DCS or PLC controller first.
So you distribute the control intelligence out to the devices.
Exactly. This can potentially reduce the load on the central controller, improve loop response times for local control, and allow for more sophisticated control strategies. It also simplifies wiring, as multiple devices share the same pair of wires, the bus or segment.
Sounds powerful. What are the trade-offs? Why isn't everything Fieldbus then?
There are significant trade-offs and complexities. First, installation requirements are much stricter than for HART 420 milli. Fieldbus requires specialized, conditioned power supplies, carefully designed network segments with specific terminators, segment protectors, and adherence to strict rules about cable lengths, number of devices per segment, and shielding to maintain network integrity. Design and commissioning require more expertise.
So more complex to design and install correctly.
Definitely. Second, the communication speed, while digital, is often slower in terms of basic process variable updates compared to the continuous analog 420 MA signal. While FF has scheduled communication for control for very high-speed critical safety loops, some engineers still prefer the deterministic, simple robustness of the hardwired 420 MA signal that HART retains as its backbone.
Okay, and cost.
The initial cost of field-bus devices and infrastructure can sometimes be higher, although the savings on wiring, using one pair for many devices versus one pair per device for 420 MNO, can offset that, especially in new installations. Training requirements for technicians are also generally higher for FF.
So it sounds like HART is the pragmatic workhorse, great for leveraging existing infrastructure while adding smart capabilities. Fieldbus is the more powerful, data-rich, control-integrated option, but requires more upfront design, specialized hardware, and expertise better suited for new builds, where you can design the network from scratch and really leverage the distributed control potential.
I think that's a very accurate synthesis. The choice often comes down to that exact question. Are we optimizing an existing system incrementally where HART excels, or are we building a brand new, future-focused, data-intensive system from the ground up, where Fieldbus might be the better long-term bet?
Excellent comparison. Okay, before we wrap up, let's try to bring all this together into practical application. If a design engineer is sitting down, faced with measuring temperature for a new process, possibly feeding into an MVPT, what are the final key decision factors they absolutely must weigh when choosing between RTDs, thermocouples, thermistors, and the smart integration methods like HART or Fieldbus?
Right. It really boils down to navigating a series of critical trade-offs based on the specific application needs.
What's first?
First and foremost, you have to match the sensor to the required temperature range and accuracy. This is often the biggest initial filter. If your process operates from, say, -100 degrees C up to +200 degrees C, and you need high precision for quality control,
RTD is the likely choice.
almost certainly, likely a PT100, probably 3 or 4 wire depending on the accuracy needed. But if your process involves a furnace running at 800 degrees C or 1000 degrees C,
You have no choice but a thermocouple.
exactly. You're forced into using a thermocouple, probably a type K or maybe a noble metal type like S or R, simply because only they can survive that heat. You accept the lower intrinsic accuracy and potential drift because range is the primary driver.
Okay, range and accuracy first. What's next?
Second, you absolutely must consider the process environment and the physical installation constraints. Is the measurement point subject to high pressure, severe vibration? Is the fluid highly corrosive?
How does that influence the choice?
Thermocouples, being basically just welded wires, often inside a metal sheath, tend to be inherently more rugged and vibration resistant than the more delicate coil structure inside an RTD.
Okay.
If it's high pressure or corrosive, both sensor types will almost certainly need to be installed in a robust thermowell, but the choice of thermowell material and design becomes critical. And as we discussed, the RTD might be slightly more susceptible to damage from rough handling during installation into that thermowell.
And the thermowell itself adds complexity, right? You
Correct.
mentioned wake frequency.
Absolutely. The thermowell sticking out into the flowing fluid is subject to vortex shedding, basically. The fluid swirling around it creates oscillating forces. If the frequency of this vortex shedding matches the natural resonant frequency of the thermowell,
It starts vibrating.
it can start vibrating violently, potentially leading to fatigue failure and breaking off in the pipe, a major safety hazard. So engineers must perform wake frequency calculations based on fluid velocity, density, viscosity, and thermowell dimensions, according to standards like ASME PTC 19.3 TW, to ensure the chosen thermowell is safe for the application.
Wow. So even the protective sleeve needs careful engineering.
Critical engineering.
Right.
And another installation detail. Ensuring good thermal contact between the sensor tip and the bottom of the thermowell bore is vital for accurate and fast readings. Even a tiny air gap creates thermal lag, slowing down the measurement and potentially making dynamic compensation ineffective. Spring-loaded sensor designs help maintain contact.
Okay, so environment, installation, thermowells, what's the third factor?
Third is the desired response time. How quickly does the temperature measurement need to react to changes in the process?
Right.
If you're measuring the temperature in a huge storage tank where things change very slowly over hours, the slower response time of an RTD, especially inside a thermowell, is probably perfectly fine. But if you're measuring the temperature right at the outlet of a fast chemical reactor, or in a combustion control application where temperatures fluctuate rapidly, you might need the much faster response time offered by a thermocouple, particularly a smaller diameter or exposed junction type, if the process allows. Thermistors are fastest, but usually ruled out by range or linearity issues for these kinds of applications. Speed dictates the choice here.
Range accuracy, environment installation, response time. Anything else?
And finally, overlaying all of this, especially when selecting the transmitter, is the required communication protocol and system integration.
Heart versus field bus, etc.
Right. Does the plant already have a standard? Is it a heart-based system where you need that 420 min backup? Or is it a new field bus installation where you want the full digital benefits and maybe control in the field? The chosen smart transmitter must speak the same language as the overarching control and asset management systems.
So it's a complex decision tree balancing all these factors: the physics of the sensor, the mechanics of the installation, the speed needed, and the digital integration strategy.
Exactly. There's rarely one perfect answer. It's always about finding the best compromise, the optimal solution for the specific requirements of that particular measurement point within the overall process. #TagOutro.
Wow. What an incredibly detailed deep dive. We've really journeyed from the fundamentals right through to the sophisticated integration.
We covered a lot of ground.
We started with the basic physics, didn't we? How the electrical resistance of platinum changes reliably with heat for an RTD.
Or how that fascinating Seebeck effect generates a tiny voltage just from the temperature difference across two dissimilar metals in a thermocouple.
Right. And how thermistors offer that huge resistance change over a narrow range. These foundational principles are captured by our three distinct sensor types, each with, as we discussed, its own unique package of trade-offs in stability, speed, range, and accuracy.
And then we saw how those raw, often imperfect signals, the resistance needing lead compensation, the nonlinear millivolts needing CJC, are fed into the smart transmitter.
The intelligent interface.
Exactly, which performs that crucial integration and correction. It handles the linearization using stored curves or equations. It performs the cold junction compensation electronically, ensuring the data it outputs is clean, stable, accurate, and standardized.
And finally, that corrected, standardized temperature signal, along with the differential pressure and static pressure signals, gets fed into the brain, the multivariable pressure transmitter, the MVPT.
Right. the powerful calculation engine. And inside the MVPT, the temperature data is integrated with the DP and static pressure using fundamental fluid dynamics equations or steam tables.
To perform that critical dynamic compensation.
Yes. Adjusting the density calculation in real time based on the actual instantaneous pressure and temperature. This allows the plant to get that real-time, actionable, and highly accurate economic and safety data, like true mass flow or energy flow, often accurate enough for that critical custody transfer we talked about.
So the big takeaway here for listeners, I think, is that when you look at high-stakes industrial operations, power plants, refineries, chemical facilities, they aren't relying on simple glass thermometers.
Not even close.
They're relying on a deep understanding of these sophisticated measurement chains and, crucially, on navigating the inherent trade-offs embedded in the material science and physics of these sensors. Is the long-term stability and precision of platinum in an RTD worth the higher cost and slower response time for this application?
Or does the extreme temperature range and sheer ruggedness and speed of the Seebeck effect in a thermocouple mandate, accepting its lower intrinsic accuracy and the need for careful CJC and drift monitoring? It's always a balancing act.
We've seen just how vital that dynamic compensation within the MVPT is for maintaining accuracy by instantly adjusting calculations based on fluctuating process conditions. So let's end with a thought to mull over.
Okay.
Consider the immense, potentially cascading economic impact. Imagine a major power plant maybe selling $10 million worth of steam energy per day to industrial customers.
A realistic number for a large facility.
Now imagine their core energy flow measurement system lacked that dynamic real-time compensation. Maybe it used an older system with a fixed, assumed average seam density based on nominal pressure and temperature.
A common scenario in older plants, or if the temperature sensor fails and the system reverts to a default.
How quickly could a small, uncorrected error in temperature or pressure leading to maybe just a 1% inaccuracy in the calculated mass flow scale up?
Well, 1% of $10 million per day is $100,000 per day.
Wow, $100,000 a day.
Compounded over a month, that's $3 million in inaccurate billing. Over a year, potentially $36 million lost or incorrectly charged, just from a seemingly small 1% measurement error caused by not accurately compensating for real-time conditions.
Or flip it around, maybe it's not billing, but controlling a critical chemical reaction where the wrong feed rate due to miscalculated density leads to off-spec product or even a safety incident.
Absolutely. The consequences can be enormous. Understanding that the difference between profit and loss, or between stable operation and potential disaster, can literally be measured in the precision of a 4-wire RTD signal being correctly compensated and calculated by a smart transmitter and MVPT, well, that's truly appreciating the hidden complexity and critical importance of the industrial measurement world.
A sobering but powerful thought. Something to definitely mull over until our next deep dive.